So, what did we saw last time? Last time we saw, uh, al- yes, last time we saw Kruskal's and Prim's algorithm, and Prim's. Which one of this was there where we were sorting these edges, E1 to M, sorting them with weights, and then we were adding them as and when without forming a cycle. So which algorithm was this? Kruskal's. Okay, good. I forgot now. Okay, so now I told you, so it is about implementing this particular algorithm, but forget about that. We're going to learn about a data structure which is useful in, so if you remember what was happening, so at any point of time you were maintaining a forest, right? And if you had an edge which was between two components, you needed to combine this component, right? So this leads to what is called union find data structure, and I will tell you what kind of operations this supports and how fast can you do, okay? And the reason of using slides and not teaching you is because at least the early first part of the lecture is better explained with slides, because then there are pictures drawn. I don't have to do it with my hands, okay? Okay, but I'll give you the proof for this by hand because the proof in the slide is useless. Okay, okay, that is like proof of 80s. We'll do proof of, okay. Is it visible to all of you? Can you see these slides? Okay. So what is disjoint say data type? So we will have three operations. And what is the three operations? Make set X, which just creates a new set containing an element X. Okay? And what does find X tells? So imagine that you have these components or these sets which are disjoint, and every set will have a leader or a canonical element. So I'll say, when I'll say find X, then what does it mean? It means give me the leader of this set. Okay? And what does union XY means? So why are we using this X as a leader? Just to remember, oh, this is a set which contains X, this is a set which contains Y, and whenever I say union XY, I would like you to give me a set containing all the elements where X was a leader, containing all the elements where Y was a leader, and again, now define a leader of this new set, union of these two sets, okay? Replace the sets containing X and Y with their union, okay? So notice M is like number of calls to make set, find and union, and N is a number of elements, like number of calls to make set, okay? So basically suppose I have N number of elements, but I could have many number of calls to make set, find and union, okay? Or find with this. So there could be a sequence of lots and lots of operation. Now where it is used, like for example, dynamic connectivity, right? So you're given initially an empty graph G, and I would like to say, okay, add node, okay, add node, add edge UV. It means now you have to look at U and look at V and add this edge. And what is so this is like a make set operation, right? Right? And add edge UV, add an edge between nodes U and V. It's like you are adding an edge between two things, okay? Is connected UV, is there a path between U and V, right? So this is like, it will take two find operation. What is a two find operation? So what are we going to maintain here? We are going to maintain add edge UV whenever I say to you. These are like, I'm going to store, like save connected components, okay? Now, what is connected UV? I will say, look at the set which contains U. So basically I will give you a pointer to U. Now you have to return me the leader of this, okay, you gave me. Now I have a pointer to V. I said, give me the leader of him. If both have them the same leader, then by the property that we are maintaining a connected component, so every set of vertices is nothing but a connected component, right? Suppose this is an invariant which we would like to maintain, then it is very easy, right? So when a node comes, I just add it singleton. This is the first time a node has come, so I just add it as a singleton. When a new edge UB comes, I just check like union operation. All I have to check what? When should I add this U? Like if U is already there, V is already there, right? But if U and V belongs to two different connected component, then I have to do union of these things, right? But if they belong to the same connected component, I will do nothing. This is the way I can maintain connected components, right? So this is why make set operation, union operation, and two find operations will give me things. So I can maintain dynamic connectivity using this approach, and this is what we were trying to maintain in the for the implementation of Kruskal's algorithm. Am I right? So now let's see how are we going to implement this. Okay, so this lecture is all about implementation of this particular data structure. Okay. So these were the original motivation for people for disjoint data type. So this comes from this is like 1964 paper which introduced key data structure for this problem by Bernard Eggelard and Fisher, like basis of like equivalence, right? So if you wanted to store something based on their equivalence, right? So what is an equivalence here? We use, two things are equivalent if they are connected, right? But I could have defined a different notion of equivalence, and I would like to store each equivalence classes in one thing. So if you are going to merge two equivalence classes, then you have to just merge them into one. So this is where it comes from, right? So you can think of each connected component being vertices which are in the same equivalence classes. And what is my equivalence relation? U is connected to V. So notice if U is connected to V, U is related to V and V is related to W, U is also related to W because there is a path from U to V, there is a path from V to W, so there is a walk from U to W, but whenever there is a walk from U to W, I can derive a path from U to W, right? So this is an equivalence relation. Okay? So this is the original motivation for people to come up with, and this has found lots and lots of application in. Okay, things doesn't work. Maybe this is less battery. Okay, Kruskal's component, connected components, computing long like LCA entry. Like what you know what the LCA is? Lowest common ancestors. Okay, checking flows graph for reducibility, equivalence of finite state automata, blah 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 blah. Several applications. So all I'm saying, this data structure is very important. So Kruskal's. So like think about this. Whenever you want to maintain things in equivalence classes, think of this data structure. Okay, that's a way to look at it, right? Okay. So let's look at the first naive linking. Okay. Komal, I'll send you the slides. Okay, I will tell you where you should take notes. Okay, I'll tell you precisely. I'll send you guys slides. Okay, so that you can just look at it. Okay, it's really easy. This is why I'm using slides, because once I explain this to you, you will be able to browse through. Right? You don't have to read the book. They are very well made slides. I didn't make them. I just requested them and they gave me. So last night I asked them that I really like your slides. Can you give me? So they gave me. Fine. Okay. So we are going to do what is called reverse tree representation or parent-like representation. So I'm going to represent each set as tree of elements. Okay. Each element has a parent. Okay. Okay. Has an explicit parent pointer to the tree. Right. So look at this, and the canonical element or the root of this tree will have a self loop. So he doesn't point to anyone. Right. So this guy is going to serve as a what is that called? He is going to serve as the canonical element of this set. Okay. And it points to itself. Everybody points to its parent, but the root or the canonical element points to itself. Now, what does it mean? So I have a tree here. I would say, oh, take union of 3, 5. What is the meaning of this? Please take union of set that contains 3 and the set that contains 5, right? Take the union. So now I have stored them as trees. What is the canonical way of doing this? I will, so parent, so first I find parent of 3, or first I find the canonical element here. So I found 8 and 5, this is root. What should I do? I should just make one of guy point to the other guy, and that's it. So what I've decided that I just take root of one guy and make him point to the root of the other guy arbitrarily. So this is what I mean by naive implementation. I don't care. Okay? All good? Right? So if it is tree, this is what you do. See? This is so easy on slides. Otherwise I have to draw them. Okay. So disjoint set data structure can also be represented as arrays, but let's forget about this representation. This is useless for our purposes, so I will not talk about it. Okay, so we go back to naive linking. So what is the naive linking? Link root of first tree to the root of the second tree. This is it. So I give you 2 trees, union 3, 5, then you have to take this, link him to the root. That's it. Right? So what is union 5, 3 will mean? I have to make him link to him. Right? Because look at the set which contains 5, make him the child of the root of the second guy. This is what my naive link root of the first tree to the root of second tree. Right? So this is my current implementation. And what is make set X? So whenever you have to make set X, I just make a node X, like one node, and I make a self loop to itself. So like it's a parent of itself. So I have created a node which is like a single node tree. So what it should do? He is a parent of itself because he is the root, he is the only child. Okay. And now how do you find X? What do we need to return find X? I need to return the canonical element, which means I need to return the root. So what should you do? Just take him. If he has a parent, go to him. If that guy also has a parent, go to him. If that guy also has a parent, go to him. So you go until you find a node who is a parent of itself. And the way we are maintaining this tree, what is the property? We are maintaining an invariant that the only root or the canonical element has the property that it is a parent of itself. So this is canonical. So everybody just goes on and finds its root, right? So this is how I will find. So while X is not its own parent, X is assigned parent of X, and we just return X. So this is how you loop in, right? So for example, okay. So here, if I ask you, okay, find 6. What is the meaning? You need to return it. So you will go, what is the parent of 6? 5. Who is the parent of 5? 7. Who is the parent of 7? 8. Who is the parent of 8? Itself. So then I return you 8. Okay. And what is union of xy? So we are doing naive linking. So first I find R, which is find of x. So I have found the root of the tree which contains x, S, which is find of y. And then what I should do? I make parent, like who is a R, so I have to link S to R. So what is S? Who is the parent of S? Is a parent of R. Okay. Okay. So now notice what could happen in this naive linking. Okay. So my point is a union or find operation can take as bad as linear amount of time. Why? Because look at the following sequence of operation. Right? So in the worst case, find can take you time proportional to the height of the current tree. And if I can show to you that there exists a sequence of operation, yes? Very disruptive people. Okay? So what I do, So first I introduced what I do. What is the height of this tree? Is 2. What is the height of this tree? 1, 2, 3. So this is 3. But suppose I have first added 1, 2, 3, 4, 5, 6, 7, n. So I made them singletons. Now I do union 1, comma 2. So 2 is going to go and point to 1, right? What is happening here? Have I done something wrong? Link root of the first tree to the root of the second tree. Oh, this is the problem. Okay, so we are making first guy the root to the second guy. Sorry. So this is why all of the things are just coming. Yeah, this is why S becomes parent of R. Fine. Okay, correct. Right. So we are making first guy be the, so 1 to 2. Now I have 1 to 2. Now union 2 comma 3. So 2 is a leader, 3 is a singleton, right? So 2 goes and points to 3. Now I will do union 3 comma 4. So 3 is a leader and 4 is the second guy. So 3 goes. So you can get a path of length n minus 1, right? So if I do naive implementation where I say, please take the root of the first tree and make him point to the second tree, it could happen that I could get a very skewed tree, like just like this. Now if I ask you to do find, right? If you find 2 or find 3, it could take as bad as n.
You can mute their audio, I think.
I don't know why should someone teach these people. Okay, so I'll write an email. This is okay. So this is what is called naive linking, right? I have naively linked, right? So if you naively link, things can be very bad, like, but we would like to do a little bit better. So what is called, let's link by size. I said let's not link arbitrarily, but let's link by look at the size of each of the objects, and let's link lighter to the heavier. Okay, then let's see what happens if we apply this heuristic. Do we do something better? Okay, maintain a size tree, like number of nodes for each root node, okay, and link root of smaller tree to root of larger tree, breaking ties arbitrarily. Okay, so here, so I can maintain a size invariant very easily. So whenever you are creating a set, what is its size? 1. And whenever you are merging two things or taking union of two things, what is the new set? New size of this, at this root I can store this plus this, and that's it. So this is a very easy invariant to maintain. So here, what will happen? So now I have 5, 3. I look at 5. 5 is here, 3 is here, but who will link to whom? This guy has a smaller size, so I should link him to the other guy. That's it. So now, and I update the size. So whatever our size here plus this size is the new size of this tree or the set. Okay. So now, this is how, if you maintain a tree size, now our new code will look like as follows. Parent of x is x in the make set, size of x is 1, and find of x remains the same. While x is not a parent of x, keep going on. So this is maintained. But now, union, we have a caveat. What is the caveat? We say R is find of x, S is find of y. If R equal to S, then just return. Means maybe what happened is that I want to, like, they belong to the same tree. Look, I gave you x and y and you have to, but they might belong to the same set. So what will union should return? Just return, if R equal to S, just return this itself, okay? Else, if size of R is larger than size of S, then what should I do? R becomes parent of S. So I have linked. And what is his size? Just sum them up. size of R plus size of S. And what is size of R stored? The total number of nodes in the tree. Okay. Else, in other case, I don't care. Either S is larger or equal. I don't care. In either case, I make S the parent of R and I just update the size. So this is what link by size. Now, what did we achieve by doing this? Simple change in implementation. Before, we never cared how we added, but now we say, look at the two trees. We only link a smaller tree to the bigger tree.
Shouldn't we be maintaining the height instead of size?
Let's have patience. Okay. So use link by size for every root node R. Size of R is at least 2 to the power height R. And that is very simple because if you notice what is happening. Do you have a question? So we are going to apply induction on number of links. So what is a singleton tree? Has size 1 and height 0. So 2 to the power 0, which is 1. So this is perfectly valid. So induction hypothesis assumes that after first I links, tree rooted at R, right? Assume that this is true for all this. Now notice that tree rooted at R changes only when a smaller or equal size tree rooted at some other object is linked into this, right? When a smaller or equal size tree rooted at S is linked into R. True? So first let's assume that height of R is strictly greater than height of S. And I told you what means, right? So because this is what we are trying to prove. Then what is the size prime of R? Size prime of R is greater than size of R because we are linking thing. Look, what I'm saying, if height of R is greater than height of S, so R is much more. So that itself has already lots of nodes, so I don't care. By induction hypothesis, right, if R, look, we are applying induction on this. If this guy itself is large, so look, what is size prime of R? Sum of this is greater than size which is already at R, then that is already 2 to the power height R by induction hypothesis, which is equal to 2 to the power height prime of R. Because height is not going to change. If you notice, if height of R is greater than height of S, and if I map them, height is not going to change. Because maybe it is R minus 1, so when I add this, it can become equal to R, right? But if the guy whose size is larger, his height is strictly larger than the other one, then his height is not going to change by adding this. And this is what we are using here, right? So this is why you can write this is equality. Look at the new tree. It has some size. What we have to show that number of objects here or the tree has 2 to the power height of this guy, which is same as height prime of the new leaf. And this happens. What is the second case? Okay. Height of R, where, look at this, this is the picture which will tell you, right? Okay. Notice what happens. Here, what is height is 2. Here, height is 1, right? But when you link them, height can never increase. So, already, so think of this proof as being, what I have to show? That the total number of object here is 2 to the power height of R, right? So, before this itself, it had 2 to the power height. So when I add it, I can only get more. So this is it. So this is like one line idea. But secondly, imagine that this has a smaller height than this, although the size is larger. So now, what is size prime of R? Is size of R plus size of S. And what is the property? Why did you add this link? Because this guy was smaller than this guy. So the total number of nodes here is at least 2 times size of S. Right? And what do you know? Look, here S has a larger or greater or equal to height. So this is equal to 2 times 2, twice 2 to the power height of S by induction hypothesis, which is equal to 2 to the power height S plus 1, which is 2 to the power height prime plus R, because what is the new height? This plus 1. That's it. Okay. So what happened because of this? What happens because of this? So look, please look at this proof. This is like, there's nothing much happening, but this is the only proof which is there probably. Okay. So for every node, every root node R, total number of objects which are rooted below him is at least 2 to the power height of R. And this is very, very like simple analysis. Okay, right? That this is now. So running time of each operation is bounded by the height, right? And by the previous property, the height is how much? At most log n, right? Because look, 2 to the power height of R is less than equal to n, total number of nodes, right? So height of R is at most log n. Do you have a question? No? Okay. Okay. So this is linked by size analysis. Okay. Okay. So now we know that the height of any tree is never more than log n. So how much time will the find take now? You are given this thing and you go up, up, up till you find the root. But that is proportional to the height of this tree. And we just argued that the height of this tree is never going to be more than log n. Right? For union, you have to find two elements that will take order log n, and then you order one operation to make a pointer from here to go a pointer from there. That's it. Right? So union operation just takes order one time except for these two calls to find. So find can take order log n, but given that you have found his root, it will just take order one time to do this. Okay? Okay. Okay. So now I'm going to give you an example which will show to you that if we are going to use this heuristic where we are going to link things based on their height, then we cannot beat log n. Okay? Why? All of you have seen these binomial trees, binomial heaps. So imagine, so this is how binomial trees are made. Okay? So arrange 2 power k minus 1 calls to union to form a binomial tree of order k. And any order k binomial tree has 2 power k nodes and height k. Right? So if you do this union, right, what happens at each time? You never, like, it has the property that, look at this, 2 power k. Look, this is a singleton. How do you make B2? Do you know how do you know B2? Take 2 copies and just make one the child. So this is how we make. How did we make B3? We make 2 copies and make one guy child of this. So if we had sequence of these operations, what will we achieve after this? Right? I would have given n. And what I'm doing, this is precisely what both are equal. So you could have just mapped anybody to anybody, right? But now, so imagine that now, so imagine that I have 2 copies of everybody. Like I have 1 copy of everybody, or yeah, so I have 2 copies of everybody, 2 copies of first, then 1 copy, like 2 copy of first and then 1 copy of each. So I first combine these two, get 1 copy. Then I say, hey, combine him to him, get another copy. Combine him with the other one to get another bigger height, so on and so forth till we get Vk. Right? But now this has height k and we have applied the sequence of operation and we have maintained the invariant that we are taking the, we are doing, we are implementing the heuristic that we are pointing smaller size set to the larger size set. And when they are equal, we do not care. Okay, so this becomes tight. And now let me tell you which is what we will use most of the time. It's called link by rank. Okay. So link by rank will maintain an integer rank for each node. Okay. Initially it is 0, but now we'll say link a root of smaller rank to a root of larger rank, and in tie just do arbitrarily as before. Okay. So in the beginning, rank looks like height, but you will see as we progress further, rank is not height. Rank is entirely different object. Okay, but it is motivated from height. Okay, okay. So for now, rank is height. So what I'm saying, what is union 7, 3? 7 is here, 3 is here. This guy has a smaller rank compared to this. So then what will I do? I will make him point to him. So now I do not care about the sizes. All I care about, look at the root of these two guys. Whichever is a smaller rank, make him point to the guy with a larger rank. Okay. So in the beginning, as I told you, rank and height are the same thing. But we will see what happens. Okay. So now Mika said, what is the height of single element? 0. So it coincides with the definition of height. Find x still remains the same procedure. So like go till you find. But union is also fine. I find R, I find S. I will tell you where things changes. Okay. If R equal to S, if rank of R is strictly greater than rank of R, then what I do? R becomes parent of S. But now, here, if rank of R is less than rank of S, then parent of R, S becomes parent of R. So if they are less, strictly less, then I put them. But if you notice, I have done no changes to the rank up until now. No changes to the rank. But else, when I do, when two guys of the same rank, we are going to merge or we are going to take union. Then I arbitrarily made like what S parent of R, but what is the rank of S? Rank of S plus 1. Okay. So let's pause and spend some time. So do we have a duster here? Okay. So what does it tells us? I have a tree. Okay. Suppose this is R and suppose this is S. Okay. If rank of R is strictly less than rank of S, then what we do? We added him like this. Okay. And no change in rank of any objects. Again, I should not make. Like this is what happens in this case. In this case, what will happen? S will point to, R will point to something, doesn't matter. But if they have the same rank, what did I do? I took R, made him point to the S, but I updated his rank of S equal to rank of S plus 1. Okay. So suppose if I had an invariant that the rank of this tree, highest ranked element of this tree is the root and it is unique. Suppose, right? then it is maintained, right? Why? Because look, this guy was unique here and the highest ranked guy. This guy was unique and highest rank high. But when I added these two guys, there are two guys of the same rank. But if I updated him, I have made him difference from him, right? Anyway, when I said all other guy has strictly less rank here, like less rank, less, like strictly less rank, then what is the property of this? Now still have this property because everybody had, I only have increased, I have not decreased, right? So if all of these people had, suppose this was quantity 10 and this was 10. So everybody had less than 9, everybody had less than 9, right? But now only people, now what I did, I added 1 to it, 11. So of course everybody has strictly less than, and everybody had strictly less than this itself, and this itself is less than him. So this is, right? So this is the kind of properties which rank has, which we will exploit nicely, okay? So now let's look at what did we achieve using this rank. Do we have, again, can we do find operation in logarithmic time? Is it obvious to see from here? Can you tell me some relation between rank and height? My claim is this happens. Rank is always less than or equal to height. Inductively, you can prove.
Take 3 cases or two.
You just,
You take the 2 cases of.
no, like base case is correct. Rank is equal to the height. Look at when you add things, right? When you add this thing, right? So when you add here, like what is the property here? Height. And this, look, suppose this was 10 and this was 11. So what we did do? 10 and we added 11 here, right? What was the property here? Now what could be the height here? Huh? Yeah, so this is 10 and look, this is higher guy, right? Maybe, so I added 10 to 11, but now what is the new height? What is the new height? It's still 11, right? Because this can only add 1, which is 11, so that's perfectly fine. And when they were equal, and then height could have increased, and I also increased the rank, no? Right? So this property is preserved. So if I can show something nicer, so rank is less than or equal to height. Okay. Okay. And if I can also show to you that look at any guy and look at the path to its root, all the elements it will encounter have distinct ranks. Suppose I show this to you, that I look at any x and I go to the root, all the elements it encounters, their ranks are distinct, right? Their ranks are, first of all, they are distinct and larger than him. Like, so every parent, like parent of everybody, if I can show that parent of this guy has a higher rank, greater or equal to higher rank than him, then that's perfectly fine, right? So I encountered him, strictly greater rank, and this guy has also strictly, but it could be strictly greater, could be like, here I have rank is 2, it could be 5 here. All I am saying is strictly greater rank, right? But it could be 5 here, I'm not saying it is 3. Oh, next parent strictly has higher rank, fine, 9, 11, 23, blah, right? Whatever this number, 57. But what do I know? Rank is less than or equal to height, and all I have encountered here is some distinct objects. So it is And that is why we will be able to show this. So that's a property of the rank. So now let's look at these beautiful properties of ranks and try to utilize this for our algorithmic purposes. Okay? If X is not a root node, then rank of X is strictly less than rank of parent of X. Why? A node of rank K is created only by linking two roots of rank K minus 1. Right? So like this is the only time when you create, right? So whenever like two guys have same rank, now someone becomes parent, then you have increased his rank, right? So this is what. So a node of rank K is created only by linking two roots of rank K minus 1. So what does it imply? Now this guy's parent is this, otherwise you do not create, but then this guy rank is anyway strictly less than him. Look, what are the two cases? You either connect him, the least, look at the previous picture. This is the only time when you are making this point, making a parent, new parent, by using this operation. When you are making here, rank of R is strictly greater than rank of S. So, and I am not changing the rank operation. So clearly my parent has strictly larger rank than me. Same here. But when they were equal, I am artificially going and making the rank of my parent strictly larger than myself. Right? So what is the invariant? Everybody's parent has a strictly larger rank than him. Okay? And if X is not a root node, the rank of X will never change again. That's true. If you are not a root node, right, then you are, because when does the rank changes? When you are the root and a two equal guy, one guy becomes. So once you become a normal node, your rank is never changed, right? So if X is not a root node, then rank of X will never change again, because rank changes only for the roots, right? A non-root never becomes a root in our operation. So just by the simple properties of our union find, what do you call this? Okay. Look, if parent of X changes, then the rank of parent of X strictly increases. What I am saying? If parent X, look at some guys, which is X, if parent of X changes, then the rank of parent of X strictly increases. The parent can only change, first of all, for a root. So before linking of parent of X is X itself. Look, so only person whose rank changes throughout the process is roots. So when you are root, who is the parent of this? Right? Itself. So that is the rank itself. But in any case, when you map, either the current parent which I am going to make has strictly larger rank than me, then perfectly fine, or artificially we increased it by 1, right? So this is what it says, right? After X is linked by rank to new root R, we have always that rank of R is greater than rank of X. This is always true. So what does it mean? If parent of X changes, then rank of parent of X strictly increases, like it's total. Okay? Any root node of rank K has at least 2 to the power K nodes in the tree. Okay? See, base case true for K equal to 0. Assume that it is true for K minus 1. Okay? Okay? Right? So, either when you add, what happens? Rank is like when either you do add, so rank of this guy is strictly larger than this. So by induction hypothesis, this itself has more than 2 to the power rank. So only time when things happens is when you added two things of the same rank. But by induction hypothesis, this is has, suppose this rank is K minus 1, So 2 to the power k minus 1, right? At least plus 2 power k minus 1, right? Because of this, so which is greater than or equal to 2 power k. Because 2 times 2 power k minus 1 is 2 power k. Right? So this is the property. Right? So this also implies to us that, look, there are many ways of showing this, right? And one way, as I told you, right, height, rank is always less than or equal to height. That is my way of looking at it. And now that we have shown that every parent has rank strictly increasing, so there are only these in many numbers, and you have to only reach, and that has an upper bound of height. So how will you have more than log n? Because ultimately from here, the highest rank of node is at most log n. That's clear, right? Yeah. So okay, this is the most non-trivial property. Okay, and this is what we will use it. So for any integer k greater than or equal to 0, right, there are n divided by 2 power k nodes of rank k. Forget it. Okay, let's see why this is true. Okay, let's take two nodes, x and y. Let's take two nodes x and y. Look at the subtree rooted at this. Let us look at subtree rooted at y. Tell me one thing, can y belong to this subtree? Can y belong to the subtree? Then here's a path to x. But on all these paths, this guy has a higher rank than him. This, how everybody's rank increases on this path. So how can y belong to this here? It cannot belong, right? Agreed? Okay. So at least y cannot belong. Look at z here. Look at any z here. So if y does not belong here, and these are trees, so can I say that this and this are disjoint? All I am saying to you, neither x is ancestor of y, nor y is ancestor of x. None of them are ancestor of each other. It means, what is the meaning of them? They do not lie on the path from each other. So it means the subtree rooted at those guys are distinct. Okay? So what did I say? Any root node of rank k has at least 2 power k descendants, property 4, right? This is with the property 4. Okay. I mean, okay. Look, any known root, any root node of rank k has at least 2 power k descendants by property 4. Now, any non-root node of rank k also has at least 2 power k descendant. Why? Because it had this property just before it became a non-root, right? Property 4. And its rank doesn't change once it becomes a non-root. So this property always holds. And its set of descendants doesn't change once it became a non-root. And different nodes of rank, same rank, can't have a common descendant, right? This is what I was trying to tell you. So what is the meaning of this? Look, suppose okay. So suppose there are p nodes of rank K. Suppose there are, say, Q nodes of rank K, right? So each of them have a subtree rooted at that, which contains 2 power k object. So Q times 2 power k should be less than equal to total number of nodes in my graph. That implies Q is less than equal to n divided by 2k. That's it, right? So this is why we were trying to say they are disjoint. Otherwise, I cannot say this, right? So for every rank k guy, I'm able to associate 2 power k nodes such that these nodes are pairwise disjoint. So that if I sum them up, they are less than equal to n. Because if they were intersection, I cannot say that they're upper bounded by n. Then I have to also take care of their intersection, how much it is, and things like that. But so look, and the basic thing to remember always is that look, they cannot be descendant. Look, rank 2, rank 3, rank 4, right? So look at this path. Every guy rank keeps changing on this. So you cannot have two people of the same rank being ancestor of each other, because then there's a path. How can you have like non-trivial path from one node to another node? And on this path, I start with one rank and I go reach the same rank, when I know that on each hop, rank strictly increases. Not possible. Okay, so that's a property. So this is the property of link by rank operation. Okay, so using link by rank, and any union or find operation takes order log n time in the worst case, where n is the number of elements, right? Because height itself is upper bounded by log n, so all of these operations will take. Okay, let me use the last heuristics. It's called by path compression. So what I do, when I'm finding a root R, I say, hey, let's do more work. Okay, when I'm finding, so I said you find X. What is your objective? You have to return me the root R. What I do, I go on the way, and every node on that path, I make him direct descendant to the root. Direct descendant. So what will I do? X becomes directly linked to R. U becomes directly linked to R. V becomes directly linked to R. And how will you achieve this? This is very easy. I can do in two ways. Okay. I go through this. I first find this R. Okay. I find this. I take this pointer, make him point to this. I keep one pointer. Then I go Y. I take this pointer, make him point to this pointer. I take this V, delete this pointer, point him to this. So basically, it's pointer chasing, right? So X to Y is fine, right? Right? So I just directly link it. Now just imagine yourself. So look, I will do everything as before, like by rank, but I also will do some extra work. Notice that still this, in the worst case, it will be like log n for sure. Right? Do you understand? So after path compression, this is what it will look like. So when finding the root R of the tree containing S, change the parent pointer of all nodes along the path to point directly to R. This is what the heuristic, path compression heuristic is. So for example, I have X. So 9, 6, 3, 1, and this is R. What will I do? I will make all of them. So how do I 9? What I have to do? I have to make him directly to this X, right? So this is what I said, that I can just go once. I have kept one pointer, and oh, this is my root. I have kept. Okay, now I just keep deleting. Now I move to 6. I moved to 3, and I said, okay, I have remembered him anyway, so I made him, and 1 is anyway linked to ring. I don't know. But now notice in the next time, immediately if I ask the question, return me find 6, how much time it will take? One step, right? Find 3, it will take constant amount of time. So what does it looks like? So when finding the root R of the tree containing X, we change the parent pointer of all nodes along the path to point directly to R. Okay? Good? Right. So shouldn't we expect that this should do much better on an average compared to, like, if I say look at do lots of operations, like after sooner or later, after some sequence of operation, everything should be much faster, right? Because once I do so much amount of work, right? Notice the intuition is, look at these trees, right? Let's look at these trees. Once you call this, you are going to use time proportional to, you're going to spend time proportional to this path and to find this, and then made everything simple. Every time you do non-trivial task, you are making this path simple. Like you are making him, after that union, everything is like order 1. The moment non-trivial task happens, this happens. Now the point is, common intuition is that how many times that, look, the problem is that, look, if I could do that, look, once you have taken this path and you made them, then this path, so suppose I want to charge every edge on this path, like number of times it is used. Like I want to sum this over all the operations. You understand what I'm saying? Let's sum this. The problem is that now, suppose I want to make 10. This edge will be again used. I want to find path from 3. This edge again will be used. So every non-trivial task could also be reusing some of the edges from the previously used path. So, but how many times? If I could just disjointly say, hey, every time you do a work, it is proportional to the path from here to here, and these paths are disjoint. Then I would have done in at most order n operations and made everybody like directly linked to the root, and then we are happy. But that doesn't happen because at times we have to do some overcounting, because some of the work, like, so some of the people will be like, but which are these edges which will be double charged? Let's try to understand. These are precisely those edges which had been made directly descendant to a root. Okay? Okay. Okay? So this is this fine implementation changes the tree structure, right? If X is not a parent of X, what is a parent of X? Find of parent X and return parent of X. Okay. Notice that path compression does not change the rank of a node. Okay. Path compression does not change the rank of a node. What I mean in implementation, not in reality. We have to prove all those properties if we apply these heuristics. So look, path compression with naive linking can still take you, require omega n time to perform a single union or find operation. Okay, let's not go over this. Okay, because that's not interesting. So link by rank and path compression. So we have the tree roots, node ranks, and elements within a tree are the same with or without path compression. Okay. Okay. So path compression doesn't create new rates, okay? Change ranks or move elements from one tree to another, okay? So notice this. This is before path compression, this is after path compression, okay? Now, we had some beautiful properties before, like some 6, 7 properties of this rank. Let's see if all those properties go through. This is fine, right? The tree root, node ranks, and elements within the tree are the same with or without path compression. Like, you do not change the structure. I have not changed the root, like I have not changed the rank anyway, right? So if X is not a root node, then I want to claim that rank of X is strictly less than rank of parent of X. I would like to prove this. But that is true, right? Why that is true? Because you looked at a subtree which had this property, and this guy only linked to the root which has strictly larger this. So anyway, this recency will hold. Agreed? So this property, if X is, this property holds, right? Because everybody hold. What did I do? I made him even a higher ranked person, I made him adjacent to than before. So if his parent had a higher rank before, this guy was like even like root, so it is a, so this is perfectly fine, and the subtree below had this property, so this property is satisfied. So this is done. Okay. If X is not root node, then rank of X will never change again. This is still true, because in this algorithm also we only change rank. How? Union is same. Look at the two guys, if this happens then this. So if you are not a root node, your rank will never change. What was the 3? If parent of X changes, then the rank of parent of X strictly increases. That is also true, because when we added, either it had a strictly greater already, or if it was equal, we made it greater by 1. Any root node of rank k has at least 2 power k nodes in its tree. What's wrong in the proof? Again, if its height was already larger, this property holds. If it is equal, then it already holds, right? I added 2 power k minus 1 plus 2 power. There's nothing change in there is no change in the proof. So highest rank of node is at most, because you can only make height, like you can only make rank smaller. And for any integer k greater than or equal to 0, there are at most n to the power 2k nodes with rank k. Why last property is true?
The rank is anyway not changing with or without compression, so the proof is still hold.
The point is, look, you made him. So look at the people who were, anyway, the people are not descendant of each other. And that's the point. The people with the same rank are not descendant of each other. So you never going to make, how do you look at, like 2 people of the same rank do not occur on the path. So they will never be done, they will be never done path compression anyway. That's the point, right? So people with this always have this property, still holds this property. So the bottom line is that whatever properties we had with respect to the rank, we still have all those properties even after doing path compression. So I don't know why it says property 1 and 3, but this is again the same thing. If parent of X changes, then strictly increasing. Path compression can make X point to only an ancestor of parent of X. That's it. So fine. So we have proved all these properties. So there's nothing much. Okay. Now let's look at. So this is going to do very, very well overall. Okay. And this is the proof which I would like to do now. Okay, and this is very non-trivial proof. Okay, so what I'm going to show to you, so let's first define what is log star n means. Okay, it should be n less than equal to 2 in my opinion, but fine. It's called iterated logarithm function. So what is log star n? Is 0 if n is less than equal to 1. Otherwise, it is 1 plus log star of log n. It means how many numbers of log I need to apply so that this number becomes less than equal to 1. This is what it means. So what is log star of n? Number of times do I apply log such that it becomes less than 1. So for example, for n equal to 1, what is log star of n? Is 0. What is for 2 is 1. And what is between 3 and 4? It is 2. 5 and 16, it is 3. And this and 2 to the power, whatever this big number is, 5. And there are no, this is the number of atoms in the whole world. So this number is practically constant. Right? So it is such a slow function. And what are we going to show? Okay, so this is proof. So we are actually going to show that over sequence of operation, okay, we are going to take some m log star n time. But I will not follow the proof from here. Okay. Okay. So what I'm going to show to you that is that, look, overall, how much union took or find took? Look, union was anyway order 1, given that I can perform find faster. So if I can find big O of log star n time, then I have improved all the operations. Right? So this is what we would like to show. Okay? So what I'm going to do to give this proof, so I want to give you a slightly different proof than what is known. And for that, so I'm going to use a slightly different functions. Okay? So up until now, we have used path compression is like compressing something to the root. But now I'm going to define a general notion of compress. So I'll give you a x and I give you a y. And I only want you to compress from x to y. Right? Think of y as a root and compress it till here. So general path compression is when y is the root. Okay? Okay. So let me write it down, couple of nice operation, and let's keep the slides here because we will like to use these properties, okay, of ranks. Okay. So what I'm going to define a general notion of compress takes x and y, two objects, and definitely y is ancestor of x. If x is not equal to y, compress what? Parent of x and y and who is the parent of x? I'm going to assign parent of y. right? So everybody is up to y, I'm going to compress. So think of this way, here it is y, here it is x, and suppose his parent is z. So what I'm going to do, take this subtree and make him directly adjacent to z. Take this subtree, make him directly adjacent to z. Take this subtree, make him directly adjacent to z. This is it. So this is what I do, right? So now that I know y, it's much easier. Like I parent of x is parent of y. That's it. So this is my one little operation. So now I have generalized the notion of compress, right? And in union find data structure, y is always the root. So if I can prove an upper bound with general set of such kind of operations, then I will also be able to prove an upper bound with a specific kind of compression operation. Okay. 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 And I'm going to define another set of function called shatter of x. Shatter. Okay, so what is this? If parent of x is not equal to x, okay, then shatter parent of x I think this should also have two parameters, no? So here, if I don't give you any parameter, it means it makes every node from x to root, okay, x to root, what? Into its own parent. Right? I deleted him. Look, what was each node was pointing to someone. Now I said, hey, point to yourselves. So, like basically, before we were taking union to collect them, now I'm shattering them to make them singletons. Okay? Okay. 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 So clearly, find of x, right? Look at if I give you find of x. So running time of this is dominated by what? Is dominated by the running time of compress x comma y, where y is the leader of the set containing x. Do you agree? Right? When you do find of x, you go from x to y and you compress everybody. So running time is dominated by this operation. So if you can forget find and we can just concentrate on compress. Right? So because anyway that is dominated by this operation. So forget about find. I'll only give you compress. Okay? So, okay. So we can analyze. Look, once we will set up everything, proof will be like one line. And earlier proofs were like, it took a lecture in itself and we have just 5 minutes. And at least I plan to finish before I leave. And I don't think it will take more than 10 minutes. So you can imagine the simplicity of this argument. But setting up rightly, and then I will give you the from which paper it comes from. Okay. So we can analyze only two operations. Okay. So thus we can analyze, or we can prove the upper bound. Thus we can prove the upper bound found by analyzing an arbitrary sequence of we forget make set, because that's take anyway order once, like n. So over any sequence of operation, it is going to take you n time. So why should we care about it? Because because we have to take the total amount of time taken divided by the number of operations, right, for amortized analysis, and we'll assume that m is larger than n. So like we don't care. So like little things we will not care. It's just that this find and union and all this, okay? Arbitrary sequence of union and compress, okay, operations. And what do we know about union? That's very easy thing, right? Union, once I gave you the thing, it takes order one time, okay? So let us assume that arguments of, okay, let's assume that arguments of every union operation operations are set leaders. Takes how much time? Order one time. Right? Once I give you the set leaders, how much time it will take? Constant time. Okay? Okay? Take a picture. You can take a picture of this side because I have to rub this. Or I can send you. I mean, it's just because if you need to go back and check now, you can check it.
How are you assuming that, like, the last statement?
What?
Let us assume that argument, like, of.
Because if I'm able to bound you log star n, the find operation, that dominates, right? Because once I give you this, it is not going to take you. Look, the costliest operation is compress, right? So I can write, rather than writing a union, write find this, right? Then it takes order one time, right? So this is what I meant, that like we could write this like that, okay? And anyway, notice once this happens, so the total running time is completely dominated by find or the compress. And plus, how many times will you make set leaders? Like do union? As many as n times. So that is only going to take order n times. So we can just forget that part. So what I'm saying that we can just focus on the hardest set of operations where we are going to spend a lot of time. That's all that I'm trying to tell. Okay? So now what I'm going to assume, okay? Now, since each call to compress okay, what is each call to compress specifies roots or specifies leader, okay? Each call to compress specifies the top node to be like top node to be compressed, right? I told you that compress X, blah, 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 right? Need to be the top node in the path to be compressed, the path to be compressed, okay? We can reorder the sequence of operations, okay? Sequence, I'm just trying to simplify my sequence, where if I can prove something, I still get an upper bound on my desired thing. Sequence of operations so that every union occurs before any compress. Okay? I'm just saying that look at this set of things, right? And first take all the unions, whatever you get, because look, paths remains the same if I take the, and then do the path compression. Because what are we trying to count? We're trying to count over all these sequence of operations how many pointers are being changed. This is exactly what we are trying to count. So if that object doesn't change in any reordering of my sequences, we are happy. Understand? So what does path compression does? It is just changes certain number of pointers. It is basically the number of pointers from him to the top guy to which he needs to change. That's it. Right? So if I can upper bound the total number of operation in terms of total number of pointers changed in the algorithm, we will be happy. So if I have an arbitrary sequence of events, and if I can reorder so that this quantity doesn't change, then we are very happy. Right? Okay. So the point to note is what? Without changing the number of number of pointers, okay, assignments. Okay, so let's just look at an example. It's not very hard to convince yourself, but let's just look at one example. So I gave you this to change. Okay, so I will first do compression followed by union, and then I will show you union followed by compression. Okay, and you can show that, okay, I just did this flip, nothing changed, then this flip I didn't. So if all I need to show for just one flip, and that should be okay. Take the same tree. Okay, so this is it. Okay, so what I want to do, first take what do you call? First I want to do union, this and this, okay, and then do path compression from x to y. This is what I want. So suppose I did this operation first. So what will I get? So first I will get these things. So first this guy will point to him, right? This is the transformation which will happen. So let me draw it here so that we can. Did I draw wrong? 1, 2, 3, 4, 1, 2, 3, 4. This is fine. So first let's do path compression here. So I want to do first path compression here. So what will you get if you do path compression here first? Notice that all these guys will start looking at him because the root of y is this guy. So what will it look like? It will look like x is looking here, right? Whatever this guy is going to look at here. Okay. Now you will have y looking at here, but his child is here, right? And this, right? This is what it's going to look like, right? And this is like those yellow guys. And this will, let's say, this is A, B. Now if you do A into B, what will it do? It will just take this guy and here is B, suppose. It just changed pointer to this. This is what it did. So now, so this is what, this was like compression followed by union. Okay. Now let's do union first. So union, because look, why this is true? Because path compression never changes the rank. So I can do union first. So I did my union first. So one pointer changing, right? But this path still remains here, right? So if I now apply path compression, now all these guys will become to whom? Notice it will not, like, this is why I'm only telling you that x to y, right? So this is why I define this generalized notion of path compression, because otherwise the normal path compression would have meant that if I take the union first, then whole thing till the root. But now I have told you between whom and whom. So that path still lies, right? So you will still be doing the same amount of pointer chasing, right? So this is the idea of defining this generalized notion of what you call compress between x and y. Do you get my point? So this is the advantage which we had. Otherwise, I cannot say in this sequence of operation that the number of point chasers are same. Do you see? Right? So this is the advantage we have of introducing this general compress x, y. Okay? Because whatever I do, these things remain so invariant. Good. So each union anyway takes order one time, so we only need to do an amortized cost analysis of compress. Okay? So since union takes order one time, we only need to focus on compress. Okay? And what is the running time of compress? What is the running time of compress? It is proportional to number of pointers assignment, reassignment or assignment, whatever you want to call, number of, actually we can be more specific, number of parent pointer assignment, right, plus big O of 1 overhead. Right? This is what the running time of compress is. Like amount of time, like it, total time is proportional to the size of the path or the number of parent pointers you are going to change and some order of 1 overhead. Okay? So what are we going to do? We are going to phrase our analysis in terms of pointer assignments. Okay? So what I'm going to do, I'm going to define T, M, and R is my, okay, denotes the worst case, okay, number of pointer assignments describes the worst case number of pointer assignments. Okay. Now what does this M, N, R denotes? Okay. In any sequence of M compression, okay, N node forest, so executed on a forest of N node, executed on a forest of, say, at most N nodes, okay, in which each node has what? Rank at most R. That's it. So what is TMNR? Suppose we had M sequence of, arbitrary sequence of compress operation over what? N node forest, right? And what is the property of this forest? The rank is upper bounded by at most R. Like rank of any node is upper bounded by R. Okay? So this is, so can we give up, we need some kind of trivial upper bound of Tm and R. For base case. Can you say something? What? Can you give me an upper bound in terms of R? Each node can change parents how many times? Each node can change parents at most R times. Because look at him and look at this, right? Every time, like every parent has a higher rank. So the total number of times you can do pointer changing is at most upper bounded by R. That is, like every node can only change pointers as many as length to its root, right? I mean, that's all. That's what you were trying to say. But I'm saying that is upper bounded by rank, right? So this is actually less than equal to NR because there are N nodes. So total, so like there's a just different way of counting. Whatever may be the sequence of operation, right? Total number of pointers that can change is at most NR, trivial upper bound. Okay? And what is the one line argument? Let's write down this proof. Each node can change its pointer, each node can change its parent at most R times, right? Because what happens? So look at the node, do not count the path in the compression. So now whatever may be the sequence of operation, I'm going to, for each sequence of operation, I'm going to charge the node. Okay? So suppose same guy comes and you told him to do something, right? Oh, this guy is going to become parent of, now who will be his parent now in this assignment? This. Maybe the next guy came and said, hey, do compression from here to some Z. So then, or to Y. So then his parent becomes Z. So whatever may be the sequence of operation be, I'm just going to charge the node for this operation, right? So over all sequence of operation, I say, hey, let's not carry. Every node has a bucket where it is charged, right? So anytime a compression happens, right, if this guy's parent had changed, please charge him. So each guy's parents can only change r times, hence the total number of charge accumulated in throughout the process is upper bounded by n times r if there are n nodes, and this is the upper bound. That's it. Is it clear? So don't look at each, we take each sequence of operation, but we have divided its hard work over all nodes. Okay? Because each parent has higher rank than the previous parent. And that's it. This is a one-line argument. There's nothing more than this. Okay, so this will form our base case. Now comes the fun. Okay, now comes the fun part. We are going to do some divide and conquer and apply this operation. Okay, and that is why we have defined all this kind of operation. Okay, so now let's fix a forest F of n nodes. Okay, now let's fix. Okay, so we are going to fix some things. Fix a forest F of n nodes with max rank R and a sequence C of M compression operation. Okay, so fix a forest F of n node with max rank R and a sequence C of M compression operation on F. Some arbitrary, I'm not assuming anything about this. And now let's use a symbol. Let T F comma C, okay, be denote the number of pointer assignments executed by the sequence. Okay? Okay? Okay. Now let me show you magic. Okay? This is my forest F. Okay? This is my forest. Okay, let me not, it's too big for our operations. Okay? So this is my forest F. Okay? Okay? I'm going to divide this forest. Okay? Let S be an arbitrary positive rank. Okay? Something. notice, look at the paths. Okay? If you hit an S here, then all the nodes on this path has S or higher rank. Agreed? Okay. So how will the world look like? So I want to cut into F plus and F minus. Okay? So actually the world will look like now. I'm going to call this F plus, and here are some subtrees hanging. Okay? These are the subtrees which are hanging. Okay? And what is the property of this? All the nodes here, has rank greater than equal to S. All nodes here has rank less than equal to, strictly less than S. We are going to call this F plus, and we are going to call F minus. Okay? Okay? So for now, just assume that we just have a single tree, otherwise you have to do this over a whole forest. Okay? Assume it wouldn't change anything if it's a single tree. Right? Just for the picture, otherwise I have to draw different cases. Okay? Now look at a compress operation. Okay? So if you can give me a compress operation of following types. So compress operation gives me X and Y. Look at a compress operation. Okay? It could either completely lie here. Don't change it. It could lie completely here. Please don't change it. Or it could lie, X lies in F minus, Y lies in F plus, and here is the path. For such comparison, I am going to write it as comparison plus some satyrs. What I am going to do? I am going to, without changing the number of pointers. This is the important point. Okay? Okay? So what will I do here, for example? So this is important. I will change this into some satyring and comparison operation in this case, but I will not change the number of pointer operation. Because look, ultimately we have to get an upper bound of the number of pointer assignments using this algorithm or in this sequence. Okay? Okay, so let's look at what happens. Like, let's look at example. So what will I do actually? Okay? Okay? And maybe suppose this is what it is. Okay? Then what will I do? Top guy, say, I will keep it that same way. So this guy will be compressed from here to here. So what will it look like? One, two, three, right? So 1, 2, 3. Right? This is what. But these guys, okay, so first I break them up like this. So what will I do? I'll break them up. I added this for breaking this symbol. Okay? Now you shatter all of them, meaning all these guys become parent of itself. So what is this? So you are still doing the same modification. Rather than changing his parent to this, you are making yourself a parent. Right? 1, 2, 3. So this is what the shatter operation will do. Notice the number of pointer changing has not changed. Right? So this is what I mean by that I can change a compress sequence into this compress and shatter. So let's write a code for this. Okay? So that it is easier to analyze, and then we are done. Okay, so what does it mean? So you understood, right? So if you're already in F plus, no changes. If you're already in F minus, no changes. But you are the crossing person, then I change you into some compression and some shatter. And what is my objective? The number of pointer changing shouldn't be less. It could increase, I don't mind. If it increases, I don't mind because I'm anyway providing an upper bound. So let me write down this modification. What is this modification equivalent to? So XYF, of course, Y is ancestor of X. If rank of X is greater than S, then what should I do? If rank of X is greater than S, so the bottom guy has greater than S, then you are very happy, you do normal compress, right? X, Y, F plus, because I know this is an F plus, okay? Okay. If rank of Y is less than rank of Y, top guy's rank is less than equal to Y, then what will I do? Good. I don't care. Compress X, Y, F minus. Okay. Else, now I have to do when in between. I assign some variable Z to X. What I do? While rank of parent of F V is less than equal to S, what should I do? V has been assigned parent of F of Z. So I just change the parent. Okay? So I run this, right? So so basically I'm trying to find this cut element. This is the guy first time which goes up because this Z has been, while this happens less than equal to this, you put this. So you have found an element whose parent has a higher rank, right? So what at the end of this loop, what will Z store? The vertex whose parent has a higher rank, or like whose rank is strictly greater than S, right? This is what will this store. So now what will I do? Now that I have found that cut element, what will I do? Compress parent of F of Z, comma Y in F plus. Okay? Shatter X Z in F minus. Right? This looks like redundant, no? This pointer looks redundant, no? Because anyway shattering from X to Z out, but we'll need this. It okay. So now suppose number of let's say, okay, let's do some computation. How many nodes are here? Let's say n plus. And how many nodes are here? Let's say n minus. Right? So n is equal to n plus n minus. Okay? Now let m plus denote the number of compress, okay, number of compress operation that involve a node in F plus. And what is M minus is M minus M plus.
That is the last element in H minus on that path, right?
Yes. What?
Z.
After this, what is the point of, what is the parent of Z? Has rank is larger than S, right? Strictly larger. This is why you stopped. Right? So what is M plus? All those operations which are completely contained inside this or which goes across. Right? And M minus is all those which happen. This is it. So just for this. Okay? Now so let's look at in this how many times you will do this pointer assignment. This is redundant, really, this is redundant. I have just written this for, what is that called? For analysis, to make the analysis easier. Otherwise, life will become, it's like whenever you have to write some recurrences, sometimes you have to subtract something, right? Do you remember? Otherwise, you cannot get the recurrence correctly. Have you noticed this? That you have to subtract, like if you do induction, alpha n square minus, so it is of that nature. But let's see how much these add. Okay, let's ask this question. First of all, let's ask how many times will you do shatter? At most n times, right? Because at most n times. So shatter is only going to add how many pointer? Right? Total number of pointer reassignments. Okay, so I'm just going to rub this. Okay, because this we proved already. Okay, magic is about to come. So hold your breath. Total number of pointer reassignment in all shatter operation is upper bounded by n. Agreed? Upper bounded by n. Okay, excellent. How many times we will do this redundant assignment? How many times? Each path compression has to go to the go. How many times this redundant operation will happen? My claim is, look, let's try to, I claim this is upper bounded by m plus. But why? It means I have to map all these operations to m plus objects, like somehow give injective mapping. But it could be, I cannot give an injective mapping to the same guy because there could be some path like this, some path like this. So we have to be careful. This is the point. Okay? Otherwise it is trivial, right? So there is something. Okay? So What is this line mirrors? What is this line mirrors? This line mirrors the fact that these are those nodes whose parent has a higher rank. Okay? Or in other words, let's write it down. So this line mirrors an assignment of the form, okay, form right? W is a parent of Z, right? Right? W has assigned parent of Z. And what is the property? Where W is a high node. So all these are called high nodes. Right? High nodes means high rank, low node. Okay? Where W is a high node, and the previous parent of Z is also a high node. Look, look at these kind of operations. How many of them are there? M plus of them are there. So this redundant assignment happens just after this. Look, when this redundant assignment, only when you are doing compression, only when you are doing a compression which goes from here to here, right? How many such operations are there? M plus, upper bounded by M plus. Only then you are going to execute this. Look, when you are going to execute this, only when you are going to compress something from here to here, right? Only then you are going to execute this assignment, right? So this is upper bounded by M plus. Now we have given injection not the number of nodes here, that is N plus, but rather number of operations, right? And this is clear, okay? So what happens? Each of these assignments, this is a simple argument, each of these assignments happens immediately after compress, right? After compress, okay, in the top forest. So we perform at most M plus redundant assignment. Agreed? Okay. So let's now, if I have to write recurrence in terms of TFC, what is this? Oh, okay, doesn't matter. What is TFC? Number of pointer assignment with sequence C. Okay? Okay? So now let's do C plus, and so this I partition into C plus C minus with respect to say M plus and M minus. That's it. So these are those operations which happens with respect to M plus, these are those operations which happens with respect to M minus, which basically, these are those operations which completely happens below and the rest of the operation. Okay, so this I tell you, look, but every operation in C++, either it happens completely inside this, or I have made an operation inside this, like a compress operation inside this, and some pointer changing, some pointer shattering or something. So this I can write it down as T F plus C plus T F minus C minus, because these operations anyway happens, plus M. So whenever I say C plus, right, look at that compression sequence. You break it into a compression here and this. So now I have divided this sequence into what? Look at C plus. I wrote C plus is like, what is, look, what is a C plus does? If you notice here, compress this into F plus. So I converted into this compression and shatter operation. So this now becomes part of C plus. So you write down, so you write C like compress, shatter, 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 shatter. So you have written down your sequence as, look at C. So look at this sequence. If it is a sequence in C minus, I don't change. But if there's a path compression in like C plus, then what I replace this with one path compression, shatter, 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 and this pointer assignment. So this is what it. Now in this, what is this? Total number of operations are whatever operations happens in F plus in this sequence, whatever the operations happens in the below, and this shattering and this pointer assignments, which is upper bounded by M plus N. That's it. So given a sequence C, I rewrote this sequence without changing. In fact, I have only increased the number of pointer assignments. If it was a compression in below path, no changes. If it is a compression in upper path, no changes. If it is a compression going across, then one up, one point and one pointer assignment and dot 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 shatter assignment. Done. Right? So shatter assignments and this pointer, I counted them separately and say, hey, for the remaining, either you are happening on the top side or in the happening on the side. So whatever the pointer reassignment on the top plus pointer reassignment the down plus whatever the other set of operations I have done. This is it. Agreed? Okay. Okay. What was the property of the top guy? How many nodes are there on the top guy? I want to get an upper bound on n plus. That's easy, right? Look, what are the top people? All have high rank. All have high rank. Okay? So this is n plus is less than equal to summation over I strictly greater than s, right? Right? N over 2 power I, which is like roughly n over 2 power s. Right? This is n over 2 power s. Yeah, we can prove this, right? N and 1 by 2 power I. Is it correct? I can take one common, or is it less than equal to? Come on, guys. N. What is A 1? Look, I is greater than equal to S. So N 2 power S gets common. What is this then? 1 plus half plus something something. No? Huh? Oh, 2s minus 1. Something of this nature, right? Agree? This is what it is, right? A 1 minus R. So A is like 1 and 1 minus R is like R is half. So half, 1, so half. Yeah, correct. So 2. So agreed? Okay, fine. And what did I wrote one theorem there. What did it say? What did it say? Each node has a rank at most R. So now you tell me how many distinct ranks are there in F plus? Because I could just think of them and reassign these guys a rank. Huh? R minus S, which is like R, at most R, right? So can I write this Tf plus C plus this is what it said, R into number of nodes, right? So this is what it is. I just used it because okay. So let's fix S equal to, look, up until now I have never fixed what this S is. So let's try to fix this S. Okay. Yeah. So let's fix S equal to something so that this becomes like this cancels out each other. This is less than equal to n. I want to do this. Then S is roughly like log n minus 1, like log n plus 1, right? So not log n, log R, because I want to cancel R. So 2 power log R plus 1 is this, right? So if I substitute S equal to log R plus 1, and this is why, just to make our maths simple, let's say this is R times n over 2 power S, okay? Otherwise you have to just carry around plus 1. It will not mix, so suppose this is 2 power S, so that I can choose S equal to log R. Then what do we have? Okay, if choose S equal to log R, then T F plus C plus is less than equal to n, right? Is less than equal to n. Okay. Now you see the magic. So now can I say T of Fc, look, I upper bounded this plus business is less than equal to right? Do you agree? Or equivalently, I can also write what is this m plus is m minus m minus, and now I can write down this minus m. I have moved this side. T f minus c minus plus m minus, no, is it correct? No, m plus what was m was m, no, m minus was m minus m plus, correct? So m plus can be assigned m minus m minus m minus. So m goes there, so this should be minus m minus, right? Let's do it. Do you agree to this? But this argument applies to any forest F and any sequence C, right? We start with, So what did we prove actually? We proved, let's say, I'm writing new recurrence, T prime M, comma N, comma R, let's see if you agree to this, is less than equal to T prime M N log R plus 2n. Okay. Now, what is T prime M N R? Is T M N R minus M. Right? What is this? What is TFS? It's nothing but, because of arbitrary sequence, this is like T of Mn comma R, T Mn R minus M is less than equal to, what is this? T Mn log R, because S is log R, because I'm in this forest, minus M minus, right? So, but number of operation, what is this operation? I mean, right here, I don't know, but at the best it is like M minus, no, N minus M minus M minus, whatever that means, that is upper bounded by. So if I substitute T prime equal to M N R, so this is like T prime of, this is like T prime M N R is less than equal to T prime M N log R plus 2n at most. Because actually this is much smaller, but I don't know. I mean, it could be that this is like whole, M minus is equal to M. So I'm just upper bounded by this. What have we shown then? Aren't we done? Look, in one iteration of 2n, I have gone from n to log r. Right? In the second iteration, I will go log of this. Third iteration, I will go log of this. Fourth iteration, I will get log of this. Voila, we are done. Okay? So this is our theorem 3. TMNR is less than equal to M plus 2n log star R. Okay? Actually, there are lots of places where, look, but to, what did we use as a lower bound here to prove this? N. Bad bound Rn, no? But now we have a better bound on M and R. What happens if we use this? Look, we use a trivial lower bound to get this algorithm. What happens if we would have used in the same argument, but here not this, but this bound? Will we get improved? Actually, yes. This is what leads to what is called, it will you can show that this is upper bounded by some 2n times Ackermann function. Ackermann function. Go and check. It is even slow growing than log star n.